Okay. So right. So today we will see the inclusion exclusion theorem. Uh, right. Fine. So you have already seen that binomial theorem and we have proved it. So just recall what was the binomial theorem. So it was x plus y. If we take power n is an integer or maybe non-negative integer here, then it is n choose 0 xn plus n choose 1 xn minus 1 y1 in this way, and the last term is n choose 1 y power n, right? So obviously if you just put x equal to 1 and y equal to minus 1, then you will see that left term will be 0 and the right term will be your n choose 0 minus n choose 1. This is just the alternative sum, and that one will be minus 1 power n choose n, right? That's mean for any n, for any n means for any non-negative integer n, it can be 0 or either natural number. Then if you take this alternative sum with that n choose 0, or you can say that nc0 minus nc1 plus nc2 minus, and then the last term is minus 1 power n ncn, then that alternative sum is 0. Okay, so we will use actually that we will use this one to prove our inclusion exclusion formula. So what is the inclusion exclusion formula? So that is very useful formula, or you can say useful theorem for to solve some problems in combinatorics. So that is very important. So first of all, we will see the proof. Obviously, I will not ask you the proof during exam, and then we will see some applications. So in exam, so some application of this theorem may come. Okay, but it is better to see the
Better to
proof
see
as
the
well.
proof.
Okay, why I am okay. So what is that formula? So if AI subset of S for some set S for 1 less than equal to I less than equal to N, then so first we take one example, otherwise it may be difficult to understand. First take N equal to 3, take N equal to 3, then A1 complement intersection A2 complement intersection A3 complement. The cardinality of this set is same as this A1 minus A2 minus A3. Okay, and then we will take that plus all possible pair, that is A1 intersection A2 plus A1 intersection A3 plus A2 intersection A3, and again take the minus. And since we have only 3 terms, so we have A1 intersection A2 intersection A3. And here better to say that here each AI and S are say non-empty finite set. Okay, or you can remove the non-empty part as well. It is 0. So you can just write that they are finite set. Okay, so we are talking about only finite case, not the infinite one. So this is the actual term. So you can generalize this term for n equal to 4, n equal to 5 as well. So in general, we will write in this way that A1 complement intersection, A2 complement intersection up to An complement. First we take cardinality of S, right? Then minus, then all possible singleton 1. So there are n terms, right? So summation this I subset of this set 1 to up to n, and it will be AI. Okay, and then there are all possible pair. So therefore it will be say ij subset of 1 to up to n, then AI intersection aj. Okay, then we'll take minus summation ijk subset of this is 1 to up to n, then cardinality of AI intersection aj intersection ak, and so on. Okay, and the last term will be so minus 1 power n. You can write here as well. Minus 1 power n and all the intersection a1 intersection up to a. Okay, so this is the formula, and obviously you can just count that. So how many elements are there in this sum? This is only n, right? Or you can say that n choose 1. So how many terms are there in this sum? It is you have n and you are choosing only 2 element set, right? So it is n choose 2. And how many elements are there in this sum? So you have n choose 3, and in this way. So right, so here you can say your nc0, and here you can say your ncn, or n choose n elements, right? Now we will prove this formula. So this is a simple formula. You have to remember this formula. Okay, so this is the formula, and we will see the proof of this one. The proof is very simple. We will just use the combinatorial argument, and we shall use the binomial theorem. So how to prove this formula? So we will see that if we choose any one element in this set in the left hand side, okay, and then we will prove that that element counted here in the right hand side only once. And if you take any element in S other than this, okay, then we will see that that element counted 0, okay, 0 times in the right hand side. So that's mean if it is counted, it may be counted twice with a positive and negative sign. So it will give actually 0. So you will see the proof, then you will enjoy probably. So here is the proof. So there are 2 steps of this proof. So first one is we show that each element of this, that is the left hand side, okay, is counted once in the right hand side. Okay, and next we will prove that each element of S minus this set is counted 0 times in right hand side. So that's mean we are done, right? Since each element of this one is counted only once in the right hand side, and each element which is outside of this set counted 0 in the right hand side. So therefore, since both sets are finite, so therefore the left hand side and the right hand side has the same number of elements, right? Okay. Now the first part, that is part 1, is very simple, and for part 2 we use the binomial theorem. So why part 1 is very simple? Because that proof is trivial. So let X belongs to this set. Okay, so what does it mean? So that's mean X belongs to AI complement for all I. So that's mean X does not belong to AI for all I. Right? Now since X not in AI for all I, so therefore you can say that X not belongs to, or directly you can say that X not in any set involving AI in the right hand side. For an example, if you look at this one, since xi is not in AI for all I, so therefore here x not in this set, x not in this set, x not in this set, similarly x not in this set, right? So therefore all these sets x is not in that set, but x is in S in that one. So therefore each element of this one counted only once in the right hand side, and that element is in only in this portion, right? Right? But x in S. So thus x is counted only once in the right hand side. Is that clear with everyone?
Sir, the right hand side is just a counting, right? So
Right,
how
right,
can
right.
we say that a particular element is counted or not? Because we are both adding and subtracting both at the same time.
Right. So what I'm saying, maybe it is just a lack of the expression. So what I wanted to say, if you are taking an element of this set, right? You are taking an element from this set, right? And if you take an element in this set, so that's mean that point, suppose x in this set, so therefore we have seen that that's mean x not in AI, right? For all I. So therefore, if you take only A1, A2, or for an example, if you take this one, A1, A2 here, so x not in the here, x not in here, x not in here as well. So here x is not in this set, so x is counted 0 times. Fine. And similarly, since x is not in A1, so x not in this set as well. So x is not here, x is not here, x is not here, x is not here as well. So that's mean if you take any element from this set, only this set, then that point should be in here only, not in any other set. So therefore that element counted only once in the right hand side. Is that clear?
Yes, sir. I mean, it's
Huh.
clear, but as per the notations are concerned, so I mean, how to write that properly?
Oh, right. So that's I will send you. I will send you the notes. That is the different issue.
Okay.
Because I cannot write each and every line here. Then otherwise, that simple thing will goes up to 2 hours. Okay. So that is the main thing here. Just understand the concept here, and then I will send you the my class notes as well. And also I have sent you one book, and everything is there in that book as well.
Sir,
Yes.
sir, you have told that by showing these two steps, this formula will be proved. So
Huh.
I'm not understand why these two steps are necessary.
Because what we are proving, see, if you are taking one element from the left hand side in this set, right? So that's when that element is counted only once, right? Because this is a single set. But here we have many sets, and there are some positive, negative, there are cardinality. Now, what is our aim? That if you take any element from this set, okay, that point, that element counted only once in here. So it may be counted thrice, but there will be some negative and positive way, so that it will be ultimately that absolutely counting will be once. Counting means absolute counting.
Okay, sir.
It may be here, here, here. Then it will be +1, -1, and again +1. So that's when absolute counting is only one.
Okay, it means like we are counting numbers from the different sets by
Right,
taking
right.
by taking this.
But since there are positive and negative signs, so our main aim is that if we take, suppose here we are counting, suppose from in this set, then we be assured that okay, that will be cancelled out from this set as well.
Okay.
So from this it is clear that cardinality of this set is less than equal to cardinality of this, because every element is there is counted only once, but we want to show that they are equal. So we will show that if there is an element in S which is not in this set, then it will be counted 0 times here. That's mean absolute counting is 0.
Yes, sir. Okay.
Since we are taking here cardinality of S, definitely there will be one element here, right? This definitely that will be here, but we have to be sure that that element will be cancelled out from some of this set.
Yes, I understood.
Okay, so that absolute counting will be 0.
Sir, can't we do this proof by induction?
Yeah, there are several ways to prove it. Since this is a combinatorics course, so even it is given in the book, I like also that proof. So this is very interesting, that counting argument. So
Yes.
whenever you see a proof, that does not mean that you have to follow that proof. There are many ways to prove a theorem. But why I prefer here the counting proof, because you might have seen some problems in your tutorial sheet or maybe in exam where that counting argument is needed. So better to learn that counting argument,
Okay.
right?
Yes.
Okay, so this part is clear, part 1. Now we will prove part 2. So if we take any element from this set, that's mean the complement of all of this one, then we will see that this is counted 0 times in right hand side. Counted 0 means absolute counting. Because obviously if we take any element from here, then that element should be in that set. So definitely there will be 1. And then we will assure that, so there will be some negation of negative of 1 as well, so that will be cancelled out. So we will prove that. So now we take the second part. Say X not belongs to that set. A1 complement intersection AN complement. But X belongs to S. Okay. Now that's mean X belongs to the complement of this one, and that is by that De Morgan's law, I think. Yeah. A to this one, right? So that's mean X belongs to some of the AI, but we don't know which AI contains X. So let X belongs to A, say I1, A I2, A I n. So these elements contains X, and X not belongs to A, say J, for J not equal to this I1, I2, Ik. Ik. Okay, so we choose some k elements from A1, A2, An. So X belongs to these k elements, that k sets. Okay, that's mean X belongs to AI1, X belongs to AI2. So there are k sets which contains X, and other of this one, other of, and if we choose that other n minus k sets, then that those sets does not contain X. Okay. Now that's mean, so that's mean here we can write that then X is counted 0 times by any term involving an a j with j not belongs to this set. It is obviously because since X not belongs to AJ, so if you take some set AJ subset intersection or something, so therefore X should not be in that set. So therefore X is counted 0 times, and X is counted once, we don't know positively or negatively. Here we write positively or negatively by each term, okay, involving only a I1, a I2 up to a Ik. This. Now note that what are the right hand side term? If you look at here, see right hand side terms are there. Now tell me X is in this set? Yes or no?
Yes, sir.
Yes, X is in this set because X is in S. Now tell me how many sets are there from this one? So here we have n sets, right? So how many sets are there from here where X belongs to those sets? So how many are there from this collection? Here we have n,
K.
k, right? Only a I1, a I2, a k, a Ik. Only those k sets contains a and other contains X, and other sets does not, right? So here we have 1 and here we have minus k. Can you tell me how many elements are there? How many sets are there?
Sir, KC2.
Right, here we will have Kc2. So we have 1, or you can say that Kc0 minus Kc1 plus Kc2. Similarly, you can say that minus Kc3, and similarly we will have minus 1 power n, minus 1 power k, Kck. And by the binomial theorem, we have seen that that is actually 0. So therefore, the absolute counting is 0 times. Okay. So I will write again. Now you write that. So there are k term of the form minus a I j for 1 less than equal to j less than equal to k. Okay, and contains x. So which counts x a total of minus k times. That is minus kc1 times. And similarly, there are k choose to terms of the form plus here a I j intersection a I k which counts x. So a total of, then it is plus k choose to times, and so on. So we can write that counting in this way the final count of x in right hand side, that is k choose 0 minus k choose 1 plus k choose 2 minus in this way minus 1 power k choose k, and we have seen that that is 0. So we are done. Okay, so by part 1 we have seen that cardinality of left hand side is less than equal to cardinality of right hand side, and by the 2 we have seen that they are not strictly less than, they are actually equal. Okay, now we will use this fact actually. So this is very useful theorem. You should not forget the statement. You can forget the proof if you want, but better to remember the proof as well, because the proof is very simple proof. This is very simple counting proof, and this type of argument is needed when you solve some problems from the tutorial sheet, or maybe from in exam when you face the problem. But remember that this time during exam we will set a relatively simple question and very related to the class notes and tutorial set. So if you follow the class note and tutorial set, you will get 15 out of 15. And if you don't follow this, then maybe you may get less marks. But if you follow, then I am sure that everyone will get. I mean, those follows class notes and tutorial set, definitely they will get 15 out of 15, because the question will be similar to that. Okay. So last time we have seen one problem, and we have and we give some argument, right? That number of solutions in terms of integers, and we have given also a lower bound, and also it was easy to tackle. Now we will give some upper bound, then we see that how to prove this problem. So this is the problem. So find the number of solutions of the equation x1 plus x2 plus x3 plus x4 equal to 25, where 0 less than equal to xi Now we will give a upper bound xi less than equal to 10. Okay, this. Now how to solve this problem? Now can you guess or can you prove it or can you tell me the procedure? How will you approach to this problem? So first you can give me any proof, any independent proof. So what is your idea how to approach this problem? So last time we have seen there is no upper bound restriction.
Sir, multiset will contain 10.
Choose n minus 1. Sorry, I got disconnected. Yeah, tell me.
Multiset will contain 10 elements of one kind. Then I think we can solve this.
So we can count the number of solutions that x1 is greater than equal to 11, and similarly another solution set where x2 is greater than equal to 11.
Right.
So
And
then like suppose a1 is the set number of solution that x1
no,
is
fine.
greater than equal
And
to
then you
11.
will use this inclusion exclusion formula, right?
Yes, sir.
Right, good. So what we will do, see, by using that inclusion exclusion formula, you can solve this problem trivially. Why? So first we take S is the number of solution. That x1 plus x2 plus x3 plus x4 equal to 25 and xi just bigger equal to 0. This is, and we know what is the number of solution, we have seen that. And now we choose ai is the number of solution of x1 plus x2 plus x3 plus x4 equal to 25, where xi is bigger equal to 0, oh sorry, xj is bigger equal to 0 for all j, and xi is bigger equal to 11. And we also have seen this one as well. Now by using S and AI we can solve this. Then in our case, now required number is, it is supposed for each I. 1, 2. I will not write here, otherwise it will give a confusion. So 1 less than equal to I less than equal to 4, we will choose A. Then the required solution is A1 complement intersection A2 complement intersection A3 complement intersection A4 complement. So this is the required solution. Is that clear to everyone? This is a required solution? Because AI is xi bigger equal to 11. So therefore AI complement is xi less than equal to 10. So therefore A1 means, so we are talking about only the integer solutions, non-negative integer solutions. So A1 complement will be only the give restriction A1 less than equal to 10. This is A2 less than equal to 10. This is A3 less than equal to 10, and this is x4 less than equal to 10. When you are taking intersection of all of this set, so it gives actually that required number of solutions. So that is equal.
So shouldn't it be like if x1, x2, x3, and x4, we have 4 variables here. Sir, why are we not doing like this, that one of them is greater than or equal to 11, or two of them, then taking the case two of them is greater than equal to 11? Like we are directly just negating that condition.
But this is a simple one, right? Otherwise you have to choose all the pairs. We are doing that one only.
Okay.
We will use that one only. But what I am saying that we are using that formula. See here we have only 4. So therefore you can do by hand, because you have only 4 choose to 6 choices for the any two. If we choose any two pair, you cannot choose. You cannot say only that x1 and x2 both are bigger than 11. bigger or equal to 11. You cannot say that. You have to choose all possible pair, right? So is that, first of all, is that clear that if we take AI equal to this, then our required number is this one, that is cardinality of this one.
Yes, sir.
Right. That is easy actually. If you right, so if it is not clear, still you can think. I think this is not one, not a big issue, because see, what is my AI? AI means, or what? Or okay, what is A1? A1 means only x1 is bigger or equal to 11. So what is A1 complement? That's mean x1 less than or equal to 10, and A2 means, A2 complement means x2 less than or equal to 10. And when we are taking intersection, that's mean x1, x2, x3, x4 all are less than or equal to 10. So that's mean these are the required number. Okay. So this is the required number. So by the inclusion exclusion formula, we know this one is same as equal to cardinality of S minus summation only that singleton set AI, now plus summation double set, then AI intersection AJ, then minus summation IJK, this set, AI intersection AJ intersection AK, and plus this one, A1, A2, A3, A4, this. Now this is my S. Now it is easy to calculate. Now what is cardinality of S? We have already seen that. So this case, so your n is 4 and k is 25. So what is the number of solution then? It is 4 plus 25 minus 1, 4 minus 1, right? So 28C3. Is that clear to everyone? Okay. Now what is AI? Cardinality of AI? The same formula. Since only xi is bigger or equal to 11, we can subtract 11 both sides, and then we will get the previous solution. Now can you tell me what is the number of this?
Seven- 17C.
Yeah, so it's just 4 plus 25, it is minus 11 and then minus 1. So it will be 17, choose 3. Now similarly, what is AI intersection AJ? Now again, you have now AI also bigger equal to 11, AJ also bigger equal to 11. Now you subtract 11 twice, right? Then the solution will be similar to only the finding the non-negative integers. Then that will be again 4 plus 25 minus 11 minus 11 minus 1, then 4 minus 1, that is 6C3. Can you tell me what is this?
0.
0. Because if we take A1, A2, A3, but any 3, say AI is bigger equal to 11, but the sum is 25, so that is not possible. So the all possible solution is 0 for any ijk, and similarly A1 intersection A2 intersection A3 intersection A4, that is also 0. Now you can put the values here in this equation. Then so total solution is, it is 28 C3 plus, and you have total 4 choose 2 elements, and each of them have the same number, right? So 4 choose 2, 17 choose 3. Oh, sorry, not this one. This one first. 4C1, and here it is 17 choose 3, right? And here it is 4 choose 2, and the number is this.
It's a minus.
Oh, sorry. This is minus, and this is plus. 4 choose 2, 6C3. So that's all. And the remaining terms are 0. So we are done. So this is the required solution. If you want, you can calculate this one as well. If you use calculator, you can use that. Or you can leave in this way as well. Okay. But I think it is better if you are using calculator, it is better to calculate this, because some of you may use a different kind of argument and it is easy to verify it is right solution or not. It will be difficult one to verify, because I prefer just use that inclusion exclusion formula. But several times I have seen students use many different kind of solutions, but that is good. When we see many different kind of solution from your side, we also learn something. Okay, so we will see that another problem that is also very interesting. So how many ways are there to assign 5 different jobs to 4 different employees, and given that every employee is assigned at least one job. Okay, so the question is, you have 5 different jobs and you have 4 different employees, and what you want to do, you want to just assign that 5 different job to 4 employees in such a way that each employee is assigned at least one job. So it might not happen that you are giving all the 5 jobs to one employee. It will not happen. Okay. So again, we will use that inclusion exclusion formula to solve this problem. Okay. So here is the solution. So let S be the set of maps assigning 5 different jobs to 4 different employees. Okay, so with no restriction. So we are not restricting that each one will have at least one job. So we are not restricting that. So this is just the map. So how many ways you can allot 5 different jobs to 4 different employees. So this is the total number. Now can you tell me what is the number? This is just counting.
5.
Huh?
4 to the power 5.
Right, it is 4 to the power 5 because you have 4 person and each person have 5 options. So therefore, oh sorry, I missed that one. I put the reverse one. Right, so you have 5. Just a minute.
Sir, is it possible that the 2 person will get the same job? Like, let's say we number the jobs like job 1, job 2, job 3, job 4, and job 5. And imply 1, imply 2, imply 3, imply 4. Is it possible like imply 1, imply 2 get the same job 1, J1, J2?
No, I did not get. So 2 different person will get the same job.
Yes, sir. Like we number like the 5 different jobs, we numbered them like in this way: job 1, job 2, job 3, up to job 5, and the 4 implies imply 1 and imply 2 is the, and then imply 4, and then if is it possible like the 2 implies like the imply 1, imply 2 have the same job J1?
Oh no, that is not possible.
Sure.
That is not possible. So that was the reason we have to first differ here the job, not the people. Okay. So that was the mistake or I was also doing here. So you have 1, 2, 3, 4, 5 places. So these are the job. Right. Now each job has 4 choices. So 4 person, this one. So one right. So each job cannot be given to 2. So it will be given only one option. So it has only 4 choices. It has only 4 choices. So you have 4, 4, 4, 4, 4. So therefore it is 4 to the power 5.
Sir, but is it possible now? Like the job 1, we have 4 choices. So let's say the choice will be even, and then job 2 we have 4 choices, which include even as well. So there
No,
may
that
be.
is see, one person can get 2 different jobs. That is fine. But one job cannot be get 2. For an example, we are here writing J1, J2, right? So here you have to choose only one choice is there. So out of 4, you have to choose one person. So you cannot choose 2 person together. Okay. But one person may have 2 jobs. It is given, na? It is given that see every employee is assigned at least one job. That means that one employee can have 5 jobs as well.
Okay, sir.
But one job cannot be given to two different one. Okay, so therefore this is the reason we have to given that these are the places that J1, J2, J5. And there are 4 places and each place will be replaced by only one. So therefore J1 has 4 choices, it has 4 choices, it has 4 choices, it has 4 choices, it has 4 choices. So therefore we have 4 to the power 5 choices. So this number can be same. So this number and this number can be same. So that's mean if this is say M1 and this is M1, so that's mean M1 gets 2 jobs, J1 and J2. Okay. Okay.
Yes, sir.
Yeah. Yeah. Thank you for the clarification as well. Now what will so this is our S, and then now what will choose my AI. So AI will be choose such that ith employee has no job. Okay. So therefore, what will be the cardinality of A1 AI? So now actually you can say that you have 3 employees because one employee will not have any job. So basically you have 3 employees only. and you have 5 job. And similarly, you can say it is 3 to the power 5 option, because again you have 5 option, 5 job, J1, J2, J3, J4, J5, and each will have 3 choices only, because one employee have no job. So therefore, it has 3 choices, and it is 3 to the power 5, and it is for all I. Right? Similarly, A1, AI intersection AJ, that is similarly this is 2 to the power 5, and similarly AI intersection AJ, A3 intersection A4, no sorry, AJ, AK. That's when 3 employee will have no job. So that's when all the 5 job will be given to the remaining one. So it has only one option. Right? Because all the 5 jobs will be given to only one, the remaining one. So that is 1. And that is not possible. So A1, A2, A3, A4, that is not possible. So this is 0. Okay. So by the inclusion exclusion formula we have, so thus required number is, so 4 to the power 5 minus 4 choose 1, 3 to the power 5 plus 4 choose 2, 2 to the power 5 minus 4 choose 3, 1 and plus 0. Now you can calculate the number. Okay, is that clear to everyone?
Yes, sir.
Okay, good. So these are the simple one actually, and there are some interesting problems. So these are the counting argument. It is better to know the counting argument. The problem is that here we are focusing only few topics, so therefore it is easy. But otherwise, if you see the general combinatorics, and if you don't have the idea, then you will find that each problem will have different solution, and there are different problem have different solution. There is no matching, and in that case, it is difficult to tackle. It is difficult to start a problem if you don't know how to approach. But here in this course, it is easy, because you know you have only that inclusion exclusion formula, and you have to use that. So it is easy. Just find.
Sir, is it necessary to use inclusion exclusion?
Yeah, we can ask, because for an example, this one, this problem, uh, you cannot prove directly, because directly upper bound you cannot tackle up the upper bound one. You can tackle only lower bound. And if you are using this concept, then you are using that inclusion exclusion formula only, right? And another option is you can use a generating function to tackle this problem. So basically, generating function, this is one way, and inclusion exclusion in one way. So there are 2 ways. But during examination, we will ask that prove it by inclusion exclusion or prove it by generating function. Why we will ask that? Otherwise, it is difficult to check the question if we don't restrict you. Otherwise, many people will have many solutions, and since 200 copies, it is very difficult to check a single question. So that is the only reason I will restrict. Okay, fine. So by this inclusion exclusion formula, you can prove actually. So another important concept, it is just a use of inclusion exclusion formula, that is called de-arrangement. That is very interesting. So that's mean, suppose you have n objects. N objects. Okay, then A so dearrangement means it is a permutation but with a restriction. So it leaves no object in its original position. Okay, and it is denoted by dn. So that's when we will denote it is by dn. In short, you can say that. So that's mean. So can you tell me? Okay, the total number, what it is? The total number of such permutation is denoted by d. For an example, what is d3? So you have 1, 2, 3. This only 3 sets or 3 elements. Okay, 1, 2, 3, and you have to give a permutation of this 1, 2, 3 so that none of them has the original place. Okay, so can you tell me what is d3? Or okay, first of all, I should tell you. So what is a dearrangement of 1, 2, 3, 4, 5? So say 2, 1, 4, 5, 3. This is a one, two, three, four, 5. Okay, so this is a dearrangement of this. You can see that this is a permutation of this one, but no elements is in the original place. But if you take 2, 1, 5, 4, 3, is this a dearrangement of 1, 2, 3, 4, 5? No, because 4 is in the same place. Is not a dearrangement. Okay, now this is called dearrangement. Now what is D3? Now you can tell me what is D3?
2.
Right, so this is just 2 because we have only 1, 2, 3. So first one can be 2, then that will be only 1, that will be only option is 2. Oh, sorry. Sorry. No. That is 3, that is 1. So that is the, if it is 2, then this is only 3, this is 1. This is only one options, and other option is it is 3, it is 1, this is 2. So this is only the 2 option. Right, so therefore D3 is 2. Now we will find a formula for Dn. Okay. So problem is find a formula for Dn. Okay, so again we shall use the inclusion exclusion formula. Proof. So let S be the all permutations of n objects. Okay, so we know what is that cardinality of S, but anyway, now what we will write? Now let a permutation have property Pi if it fixes element I. Okay, fine. Now, what is Dn? Dn means P1 complement intersection P2 complement intersection Pn complement. Why? So Pi means number of permutation where it fixes ith element. Okay, so what is Pi complement or P1 complement? So it does not fix first component. P2 means it does not fix second component. Pn means it does not fix the third component, nth component, right? So therefore Dn is actually this. Okay. And now can you tell me, so what is cardinality of S? This is simple one. What is cardinality of S? That is just a permutation of n objects. You know what is this?
N factorial.
Right, it is n factorial. Now for an example, what is P1, this one, not P1 complete, what is cardinality of P1?
N minus 1 factorial.
Right, it is n minus 1 factorial. So it is actually Pi. For any I, you can say that, right? So in other way, in short, so if you write, so that's mean for 1 less than equal to k less than equal to n, you can say that cardinality of Pi1 intersection Pi2 Pik. So that's when k it fixes I1, I2, Ik, and it does not fix others, right? So therefore it is factorial n minus k, because it fixes only k elements and remaining k minus n minus k elements can have any permutations. So therefore it is this, right? Now we can just use the simple exclusion inclusion formula. So therefore Dn means this. Okay, so that will be this one actually. So P1 complement Pn complement, and that will be by the formula. Okay, I can write the formula. Cardinality of S minus summation Pi plus summation Pi intersection Pj, then minus Ijk, subset of this Pi intersection Pj intersection Pk, and go on, and the last term will be minus 1 power n P1 intersection P2 Pn. this. And the first term will be, so that will be factorial n. That will be, first of all, n choose 0, n choose 1. Okay, and all the elements of this one will be factorial n minus 1 plus that will be n choose 2 factorial n minus 2 minus n choose 3 factorial n minus 3, and it is goes on, and the last term will be minus 1 power n, n choose n, n minus n factorial. Now if you calculate this one, then you will get, say, factorial 1 minus, so we want, so this is just the required formula, we just want to simplify a little bit. So it is factorial n, I use that factorial, by factorial 1 factorial n minus 1, so n minus 1 factorial, so that is cancelled out. Similarly here, so that will be cancelled out and it will be go on. So plus minus 1 power n, and that will be your 1 only. Okay, now you can just take minus 1 power n, take factorial n outside, then that will be 1 minus 1 by factorial 1 plus 1 by factorial 2 minus 1 by factorial 3 minus 1 power n, 1 by factorial n. So this is called the number of dearrangement of n elements. And there are some important applications of this one. Now if you remember this formula, that number of dearrangement, then there will be some problems you can solve directly. And if you can't remember this one, then you can use that simply inclusion exclusion formula, and then you can find what is the solution. Okay. So any question up to this? So basically this is the last one. So we want to stop here. So do you want to ask anything regarding this one, regarding it? If there is no question regarding lecture, you can ask regarding quiz as well. Any question, since we have time. Do you want to ask something? No? Okay, so if you don't have any question, then we can stop today. So anyway, so okay, so this is the third lecture. We will have 2 more lectures. So note that, so there will be no lecture on this upcoming Thursday, right? Because we have already taken that lecture on the last Saturday. So see you in the next Monday.